What's up, guys? This is Jahangir from Edporium, and today we're going to be talking about radical halogenation, or also these radical reactions, where we're going to have something like Cl2 or bromine, the Br2, and we're basically going to put a lot of heat or a lot of like UV light into it, and it will break those two chlorines, for example, and those chlorines will bind to a specific carbon, and that's what we're going to go into. Just how we break those bonds and how they can actually form together. So first, we want to talk about how we actually break bonds. So let's say we have molecule A over here and it's bonded to B over here. Now, there's one way that this bond could actually be broken, and it is a symmetrical break. So over here, this, I guess you could say hook arrow. So it's not a full arrow, it's just half of an arrow. This represents one electron. So one electron from this bond is moving back to the A. This one over here will move to B. Let me make that a single arrow. And when you see those single arrows, those hooks, that means that only one of those electrons has been transferred. So this is going to result in A having a radical and our B molecule having a radical. And this is exactly what radicals are. It's these like singular electrons, you could say. So over here, this is a symmetric break. So I'll do just right over here, symmetrical. And our symmetrical breaks are also going to be known as homolytic cleavage. So homolytic cleavage. So homo meaning same, lytic meaning break or lysis, same exact word. So it's going to be the same breakage and cleavage. So when you see the word homolytic, this is going to be that symmetrical break. Now the opposite of that, and that would be our heterolytic cleavage. So what would that look like is we'd have our A over here bonded to B, same exact scenario, but instead we're going to have a full arrow. Now a full arrow means that there's two electrons being transmitted. So you can think of each point of an arrow being an electron. Over here we had one point of those electrons, so that was just one electron. But now over here we have 2 points, so that means 2 electrons have been transmitted, and this will result in A having both those electrons, and it's going to have a negative charge, and B is going to lose those 2 electrons having a positive charge. So let me write this over here. This is going to be our heterolytic. So heterolytic and heterolytic cleavage, I'll just copy paste this. So heterolytic cleavage. So it's not going to be symmetric, and you're going to see these differences in charges. One of them is going to have a minus sign, the other one is going to have a plus sign. Now let's talk about how we can make bonds, and it's basically just the opposite. So over here, if we were starting with our 2 radicals, each of our molecules have one of those electrons, then we would just show it as that one arrow over here, that one over here, and that's, like we said, that symbolizes one electron. So those two are basically going to bind together, and it creates this AB bond. And over here, same exact thing, except these 2 electrons would be transmitted over to create that bond. So it's same exact thing as, we're just going backwards. So from breaking bonds, we're going from left to right, where A is going to, if we're talking about homolytic, then each of them are going to retain 1 electron. If we're talking about heterolytic, one of them is going to retain 2 electrons. And if we wanted to show how we make bonds, then we go the other way. So now that we understand how we can break and create bonds, now we can talk about radical reactions. So radical reactions are broken down into 3 steps. The first one is going to be initiation. So initiation. And this is basically when we're going to create that radical. So I'll just write this over here. If we had a bond between these 2 molecules like X and X, then our initiation step would be creating those radicals. So it might look something like this, where we have each of these molecules having 1 electron, so they have created a radical. This is what the initiation step looks like. And you have to remember that these radicals are going to be created in the product side. So anytime you see radicals on the product side, that means that that specific reaction is in the initiation phase. Now, the second phase is known as propagation. So propagation. propagation. And in this phase, we're actually going to see radicals in both the reactant side and product side. So you can think of it as like the middle ground, I guess you could say, because you're not going to see all the radicals in just one spot. You're going to see them in the reactants and product side. So what that might look like in our scenario, I'll just put organic, symbolizing like an organic molecule that we have, and this would be plus this radical over here, and then we might have an organic molecule over here plus this one over here. I'll show you guys like specific examples so this actually makes sense, but I'm just trying to illustrate how in our propagation phase you're going to see your radicals both in the reactant side and the product side. So the third phase and the last one is known as the termination. So this is the termination phase, and this is when you're going to see those radicals in the reactant side, and they're going to combine to form just like this molecule over here. This is just a specific example that we're talking about just to illustrate the fact that your radicals are going to be on your reactant side when we're talking about that termination step. And one thing to note is that the termination step is not as common, and it's one of the least common phases to be in, because the most common phase is actually the propagation phase. This is when we're going to have our molecules over here. We'll actually go through an example real quick, but our molecules are going to be reacting to those carbons in our organic molecule. So now let's actually go through a practice example, and I'll still have these phases up here just as a reminder of what we're going through. But let's say we have this organic molecule over here, and we're wanting to write down the radical reaction. We're wanting to see what this actually turns into when we add Cl2, and this HV meaning like high heat. We're adding heat, we're adding some UV light, some energy into this so we can break the bond between those two chlorines to form our radicals. So initiation phase, and 1 over here will just represent our initiation phase. So anytime I put 1, that's initiation, 2 propagation, 3 termination. So in our initiation phase, we're going to have this Cl2, so I'll just do CO bonded to Cl over here, and this is going to turn into those radicals. So Cl and Cl with those radicals. Now, how this is going to work is we're going to have our homolytic cleavage. So this guy is going to go over here, 1 electron over here, creating those 2 chlorine radicals. So that's our initiation phase right there, and we're pretty much done with the initiation phase. Now let's go into our propagation phase. And like I said, as you noticed when we were looking at our initiation, defining that, your radicals are going to be in the product side. So now, propagation. So we have this big organic molecule over here, so I'm just going to copy paste this. So we have this guy over here. And the biggest thing to note with these propagation reactions is that the radical is going to attack the carbon that has the highest classification, I guess you could say. It goes from primary, secondary to tertiary. So you want to find a carbon that's closest to that tertiary structure, meaning it's bonded to 3 carbons. So over here, we have a secondary structure over here. We can't do any quaternary structures with our radicals. We can only do primary, secondary, and tertiary. So we have a secondary over here. We have secondary all around this ring until we see this carbon over here. This carbon is bonded to 3 other carbons. So we're going to have a hydrogen over here. And this is where the name radical halogenation comes into play, because of the radical which we're dealing with, halogen. So our chlorine is a halogen in this case. So we're going to have this hydrogen over here, and you see these radicals from our initiation phase. Well, one of these radicals over here, so I'll do Cl over here, one of these radicals will actually attack this hydrogen over here. So just bring that hydrogen. The electrons from this hydrogen will go back into that carbon. So what this is going to form is we're going to have HCl, and let me just copy paste this guy over here. Copy paste, and what we're going to have over here, this carbon is going to have that electron because the hydrogen gave that electron to the carbon so it can move on to this chlorine to form a bond. Now, building off of this organic molecule over here, so we're going to have this little electron over here, and we're going to have our CO2 as well. So we have Cl, Cl. And what's going to happen is when these two break off, and one of them is going to take an electron, the other one's going to take the other, then this electron over here, this guy will actually connect all the way to this guy over here, that carbon. And this will result in a free radical over here, that Cl free radical, and we're going to have a bond of chlorine right here at that carbon. So these are the two propagation reactions that occur, but in one of them we're creating hydrochloric acid, and in the other one we're binding this chlorine to that tertiary carbon. Now, once you get a hang of this and the process of doing these free radical or these radical halogenation reactions, then you're going to know that when you see the Cl2, you just look for whichever carbon has the highest classification. So anywhere that's, if you see a tertiary, then you want to get anything close to that. It goes tertiary, then secondary, then primary, because this is what will create the most stable structure when these molecules bind, when this halogen binds to that carbon. And once you do that, you automatically know that HCl is also going to be produced because of the hydrogen over here. So it's really easy to answer these questions once you know the rules and once you get through that process. And literally practice makes perfect with these. So now let's talk about our termination phase. So termination phase, like we talked about, this is when our radicals are going to be in the reactant side. So what this is going to look like is we're going to have Cl right here, Cl right here. That's going to turn into Cl2. Now, this is not the most common step. The most common step is a propagation step. So we're not always going to be converting these radicals to Cl2. More than likely, these radicals are going to react with our organic molecule to produce hydrochloric acid or this chlorine bonded to that tertiary carbon. Alright, so for this one, I want you guys to pause this video and see if you could actually find the most stable form of this radical reaction. So this is the correct answer, and here's actually how I got through that. So first we have our initiation phase, and initiation phase is pretty easy. We're going to have that bromine, and it's going to turn into those radicals over here. So once those radicals are created, the radicals will then react with our organic molecule over here. So I'm just going to copy paste this guy over here. So we have this reaction or this organic molecule right here. We're going to have a hydrogen right here, and this hydrogen will react with one of those bromine radicals. So this is going to form our HBr, so hydrobromic acid. And over here, let me copy paste this guy over here. Over here, we are going to have that one electron in this carbon over here. So we got him right there, that one electron. And what's going to happen is this one electron will then react with our Br2. So it will react with one of the radicals. So this electron move over here, this electron move over here, and this radical will then react with this carbon over here, and this will actually create a bond at that secondary carbon. And just as a shortcut, like we said, you want to find which one of these carbons has the highest classification, so any one of them closer to tertiary, and we can't do anything quaternary. So if they're bonded to 4 different carbons, then that doesn't count because the radicals will not react to those quaternary carbons. They only react from primary all the way to tertiary. And over here we have a secondary carbon bonded to 2 carbons. So this bromine is going to react to that secondary carbon, and we also produce hydrobromic acid. So hopefully this all made sense, because I'm just going through the steps of how we went from this organic molecule plus Br2 to this bromine, which is actually bonded to the secondary carbon, and this HBr. Because all you really have to do is look for whichever carbons have the highest classification. Because if they have the highest classification, they are going to be the most stable when bonded to those radicals. And over here in this organic molecule, we had everything being quaternary, all of our carbons being quaternary besides this one over here, which was secondary. So the bromine radical would actually bind to that carbon, and we'd also produce HBr because the hydrogen would react to that bromine radical. This is definitely a concept that practice will make perfect, and as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.